Oh, just one last thing. Did I mentioned times table rock stars earlier?
Yeah.
Yeah, cool. Because it's so good.
Welcome to Thinking Deeply About Primary Education, the podcast that makes time and space to really think about pedagogy, teaching and learning, professional development, anything of interest to time-poor and enthusiasm-rich primary teachers. This week, I'm joined by Christopher Such.
Hello again.
And together, we're going to explore multiplication tables. But first, Chris, what you reading for?
Hey, what you reading for?
This week and over the past couple of weeks, I've been reading a book by Paul Lockhart called simply Arithmetic. It is a terrific introduction to the subject of arithmetic, but not in a academic sense. It doesn't feel like your standard introduction to the subject aimed at a primary teacher or a secondary teacher looking to teach. It is a way to engage with the subject in a way that provokes interest. What it attempts to do, and I think succeeds in doing, is telling the story behind arithmetic without getting too deep into the history and this sort of thing. It's still about being playful and curious with the subject, but it manages to point out all the areas where our understanding of arithmetic is somewhat arbitrary, the choices that we've made as humans around maths. In other words, it helps us to see arithmetic for what it is, which is a tool that allows us to do things, and yet it doesn't end up being purely practical in that sense. There's still this joy of the subject in its own right. I'd highly recommend it. In particular, if you're one of those teachers who teaches mathematics and is, quite likes teaching it, or perhaps doesn't even particularly quite like teaching it, but hasn't ever really had this sense of enthusiasm or really feeling the value for mathematics beyond the practical, then really check out this book. It was given to me by a chap on Twitter called Danny Yee. I think I might have mentioned this book under other circumstances last week, but check it out. So, Kieran, what are you reading for?
That's excellent. Sounds right up my street. I'm going to check it out. My list is getting longer and longer. I don't think this section really helps my reading list. So I'm going to go with a podcast. And a lot of the podcasts I recommend are history-based. And a lot of the podcasts I recommend have been recommended to me by Neil Almond. But this one is one I found myself. It's called Gone Medieval. And essentially, you've got these 42-minute chunks of historians, historical authors, sort of bridging the gap between academia and sort of the lay person, which is what I would consider myself in terms of history. And, for instance, today I was listening to two archaeologists talk about a dig that suggested the Great Heathen Army went much further north than people had originally imagined, or sort of interpreted from the sources. For instance, I think the River Tyne is mentioned a few times, but actually these guys were considerably further north. One I listened to was about how Henry VII went from an anonymous child to the sort of the King of England, and the head of one of history's most infamous sort of regal dynasties. So well worth checking out. It's got that credibility, but it's also really accessible too. So this week we're going to focus our attention, old school style, on an area of mathematics. We're going to look at multiplication tables and sort of why they're important, how we can teach them, all the things that really matter to time-poor but enthusiasm-rich primary teachers. And I think, Chris, the first question I've got for you is, why are multiplication facts and their related division facts essential?
Well, I think the first thing to note is just how ubiquitous they are within our teaching. Once they are learned, or even while they're being learned, we immediately realize that they're everywhere. So when you're dealing with fractions, percentages, proportional reasoning, they just come up again and again and again. And of course they do, because if you think of all the circumstances under which multiplication is useful, and we think about the fact that at primary school, we're not really using calculators under any circumstances. If we're going to be dealing with something that revolves around multiplication, we're going to be relying on our multiplication facts. So the fact that they come up again and again in various aspects of the curriculum is one of the reasons why they're essential. I mean, in terms of what makes learning them as facts, kind of committing them to memory essential, we go back to that simple model of memory idea, this idea that we want to be able to free up cognitive resources, free up working memory by having them committed to long-term memory so that we can concentrate on the pertinent and more challenging, perhaps, aspects of a mathematics question or a mathematics problem. The phrase that you use so often about being able to then do more interesting mathematics because you've got that foundation secure. On a slightly cynical note, the multiplication table check exists. And so teachers across the country will be thinking about how to deal with multiplication facts and the related division facts with their kids for that reason. But obviously that's not the core of why we do what we do. But I think it would be silly not to mention that. But really, it's just how useful they are, how common they come up in the curriculum. But even beyond the learning of mathematics in a formal sense, they are just a really useful bit of knowledge for day-to-day existence, being able to deal with groups of stuff quickly, being able to calculate with groups of stuff quickly without having to get your phone out, proves itself to be quite a useful thing to do. So yeah, those are where I would start when thinking about why multiplication and the related division facts are essential. What have I missed? There's bound to be bits and pieces.
I think there's one thing to say before I sort of give my opinion, and it's that we're at the precipice. You mentioned the multiplication check. It's going to now become something that schools are in some way going to be held accountable for. Certainly the people who will be able to see the data will be ourselves, potentially the local authority, and certainly Ofsted. And so Charlotte McKechnie was talking to me about how the phonics check is not the aim of the game. It's not the end goal. Right now, we have the chance to say that we're not going to make the same mistake with multiplication check. Because if we start saying how many children have passed or putting an arbitrary benchmark in place, then we invite unwelcome accountability. And I think now is the time. Much easier said than done. And I accept that it is extremely important that all our pupils know their times tables, particularly going into year 5 and 6, because of the reasons you outlined. You don't get to do the wonderful stuff with fractions and ratio if you don't know your tables. But we as a profession, particularly in primary, have the chance now to say, no, we're going to use this data properly. We're going to use this because it's diagnostic, isn't it? As far as I can remember. I mean, it's been a while since I read the paperwork because we've had 2 sort of stalled years. But it's supposed to be okay, right? These children don't know these tables. Let's do something about it and nothing more. And I really hope that it doesn't become, 75% of pupils have met the expected standard in the multiplication check, because there is no expected standard.
Yeah, and we know what schools are like with what can be like with data. Let's hope it doesn't go that way. But I think what you mentioned there about year 5, 6, it's well, the idea of saying this is a good time to keep an eye on where children are at with their multiplication tables, regardless of the check. If the government cancelled the check tomorrow, I would still say to schools, it's a really good point. End of year 4 is a really good point to know where your children are at with multiplication tables. Because like you say, the fractions stuff in year 5, and there's a lot of it, assuming you follow the rough trajectory as is portrayed in the national curriculum. There's a lot of fraction stuff in year 5. And it really comes down to, can you deal fluently with equivalent fractions? And equivalent fractions, and so simplifying, etc., and dealing with equivalent fractions is entirely based on your almost entirely based on the fluency of your multiplication and related division facts. And if you've got them down, the teaching of that bit of fractions is so much more enjoyable, and children just pick it up so much quicker. So yeah, it's a really good time, regardless of the check, to have a little think about whether kids are ready for what goes on in year 5.
And in terms of why they're essential, I think you've hit all the key markers. So I'm going to speak hypothetically. Is there an argument to be made that most of mathematics that we'll encounter, certainly in school, are just extended metaphors of the laws of arithmetic that apply to multiplication? And so you're just seeing applications of the same ideas?
I'd say a lot of it is. I'd say a lot of the stuff that relates directly to arithmetic is going to be built on, the basic operations. I mean, when you're getting into the trickier stuff where you're starting to apply, say, the distributivity of multiplication over addition, again, that stuff is just, the basis of multiplication and understanding how multiplication operates in the ways that it's combined with addition. So much of the mathematical problem solving that doesn't feel like it's related to that is, as you say, just an extension of that idea, which obviously is itself related to multiplication. I think there are obviously bits and pieces related to arithmetic that don't necessarily have multiplication at its heart, but it's so central to scaling, proportional reasoning, algebra, etc., 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 that it does feel like the heart of a lot of the mathematics, a lot of the arithmetic that comes later, and not having a bank of memorized multiplication and division facts that you can bring to bear in order to deal with that is a major impediment where it's not there.
I can't remember what it was I was reading, but it was I think it was Marcus de Sotoy, who I'm a massive fan of his work. I've mentioned him a few times in the what you're reading for section. He said about how he didn't necessarily feel he had automatic recall, and I think it's potentially dangerous narrative, because he, on the other hand, discovered a Platonic solid, and most people who don't know their times tables can't make that same claim. So I think there's a dangerous narrative around knowing and the importance of knowing. And I think we're drawing a line in the sand. The rest of your life, particularly your time in school, will be much, much more enjoyable if you know your multiplication facts by the time you're 9 years old.
And this is going to bring us on to something that I'm sure we're going to discuss later. It's like, well, which multiplication facts? Because my mum was at school. She would have been dealing with pounds, shillings, and pence. So because you've got an aspect of, imperial currency, knowing your 16 times table, for example, your 16s, your 14s, your 12s, etc., was a particularly valuable thing and was part of the required, as it were, set of facts that pupils were taught. Whereas now we stop at 12s. And again, it's something I'm going to bring up later, but I guess there is a question about, well, what do we mean? Which set of facts? Personally, when I'm thinking about this, I'm automatically assuming that we're doing what most schools do, which is up to 12 and not necessarily beyond. But again, that might be whether we go beyond and how exactly we think about going beyond that, and whether even the 11 times table and the 12 times table are as essential as the rest in terms of memorization, might be something that we get into. I guess, given that we've talked a lot in the past about number bonds, and there are similarities between the learning of number bonds and multiplication facts, a natural kind of place to go next is, what way do you think that the learning of multiplication facts and the related division facts is similar to, and in what ways is it different?
In terms of similarities, the process of committing the facts to memory is pretty similar. I think we'll definitely get to that as we go through this episode. But when I give advice to my teachers, whether they're in reception or year 6, the principles of how we're going to commit those key facts to memory don't change much, if at all. And so I think, generally speaking, they are a lot more alike than they are different. I think that the main difference that stands out to me is that when you're working with bonds, They're grouped differently in as much as 10 will be the headline, and you've got a subset that falls into that group. 5, whichever sort of sum you're working towards. And I think that almost allows you to interpret them differently, because you can subdivide them in your mind in a way that allows them to be organized. For instance, when I'm bridging over 10 mentally, I have a place in my mind where those that bond to 12 go to, because that's normally quite tricky. Whereas with your multiplication tables, obviously they will be related, but there are many, many more outcomes. And I think it's a little more difficult to say, oh, here are all my 2s in my mind, here are all my 3s, here are all my 4s, etc. And so that's how I would see them differing.
I think the essential similarity is that at some point towards the end of the process, I say towards the end, but actually it's going to take up a big chunk of time when it comes to committing these to memory, is going to involve something like flashcards. And we'll talk a bit more about exactly what we mean by that later. But effectively, here is a question. What is the answer? Not necessarily pressurized or anything, but a need to kind of commit something to memory in order to answer something relatively quickly. There'll be lots and lots of repetition, and ideally repetition that repeats the ones that you struggle with more often. What I would say, where I see the key difference, is that while both of them are built on a bedrock of meaning, of understanding, visually what's going on when you're talking about multiplication or number bonds, I think that there are the journey from that meaning to the memorization. I feel like there are more stepping stones, and that those stepping stones are closer for number bonds. And what I mean by that is, if I'm adding 7 and 5, I will teach that, or I will learn that, I should say, by doing, say, double 5 and then 2 more. Or I'll think of bridging through 10 by, 7, take the 3, add it from the 5, add it to the 7, add 2 more, etc. And it feels to me that if I'm learning my near doubles and I'm learning to bridge through 10, as children learn to do that, they then almost fall into the recall that comes after that. So you say like 5 and 7, and they go, oh, well, double 5 and then 2 more is 12. And they'll do that a few times. And then you'll see a light bulb where they're going, okay, so 5 and 7, it's 12. And there isn't like a need for the nudge as often. Whereas with multiplication tables, we tend to learn them, or we often learn them alongside things like skip counting. So, you're learning your 7s by going 7, 14, 21, 28. But to get children to go straight there and say 8 7s are 56, you need a bit more of a nudge. They'll start counting up. So 7, 14, 20. And you need to say, well, actually, no, what do you think it is? Take a guess. And it's, in other words, this leap from using a procedural level of meaning to get there is larger. It's, how do I put this? Yeah, so like I say, with number bonds, once you've got that meaning and once you've understood it visually, it can quite naturally become something you memorize once you do a little bit of flashcard work, say. I think there needs to be more of a nudge, because there isn't that bridging calculation strategy in the same way. I mean, they exist. So for example, with 8 7s are 56, a child could go via meaning and say, well, I know that 10 8s are 80 and 3 8s are 24. So 80 subtract 24 is 56. So I can get there. And again, that goes back to that distributivity principle. So you can get there from a meaning route, but is that useful? To an extent, we are going to get to a point where we just say, hang on, we just need to learn that 8 7s are 56. We've understood it in terms of what it looks like. We've understood it in terms of place value, that we're effectively reorganizing a set of 8 7s into how many 10s and how many leftovers are there. We've done all that kind of sense of meaning, but there is a bigger jump, I think, just to then going, and now we need to know it. Now we need to memorize it. That's how I feel about it. There's a wonderful blog on the subject, actually, by Michael Pershan, which is called What People Get Wrong About Memorizing Maths Facts, which is a really interesting blog. I had a bit of an interesting chat about this exact subject with him. at the time. In the end, in short, they both require a bit of flashcard work, a bit of drilling, for want of a better phrase, after a solid development of meaning. But I feel that there's more of a leap for multiplication facts. I don't feel that you can't visualize 7 sevens of 49 in the same way that someone might have a picture for 7 at 8. You know, you might be able to picture that as double 7 or one more, picturing the 2 10 frames. I don't think you're doing that for 7 sevens of 49. Or if you can picture it as 7 sevens, you're not then rearranging the counters in such to turn that into, 4 lots of 10 and 9 leftovers.
No, that makes perfect sense. Because whenever I'm talking about the 10 frame with teachers, I'm not convinced having 20 in a 10 frame is particularly helpful in terms of building up a model in your mind. I think there's too much going on. I can see why you would, but I think at that point you almost have to ask the pupils to then hold a 10 somewhere and then manipulate the other 10 and the sort of the sum left over, as you say. I really wish I'd known that Michael Persson had written a blog about this before we recorded this, because now I'm going to be second guessing everything I say, because I'm a big fan of Michael's work and his thinking. But there's such a rapid amount of change in children from 3 to 5 years old. And, you're talking about the conceptual leaps being smaller between the content and the memorization. And I think that's because almost everything they're developing, that sense of number, connects really well to the bonds. But because, if we keep that metaphor, we've got this extended representation of multiplication that gets slightly more complex every year of school, then I think it's natural that you're going to need more time to make the jump between what you're committing to memory and what you hope to one day understand. And there's quite often we have the conversation about, does memorization precede understanding, or vice versa? Because the narrative, certainly when I started teaching, was very much about conceptual understanding. But I think life is easier if you have those facts committed to memory.
Just an add, I know it's just repeating what you've said, but I think this idea of the key difference between them also being how they're organized is essential. Like you say, when you are learning number bonds, or you're teaching number bonds, I should say, you're thinking, oh, okay, we're going to be learning about near doubles. I know that they've got their doubles, so let's start using near doubles. So you're not organizing them based on, okay, I'm adding to 7, or I'm adding to 8, or I'm adding to, you're just thinking about the strategy as the way of organizing that little chunk of your curriculum. Slightly different when you're thinking about bridging through 10, because you can make an argument that that's always adding to 9, but it isn't necessarily. You might be using bridging to add to 8, add to 7, etc. Whereas multiplication facts, we're probably going to organize that around, okay, now we're learning our 7s, and now we're learning our 8s.
So Chris, then what's the relationship between learning them and skip counting?
We kind of touched on this already. It is the case that when we come to teach a certain set of multiplication facts, say the 3s or the 4s, that we introduce them by learning to skip count. So we might say 0, 3, 6, 9, 12, etc. And that tends to be a jumping off point, though if we're not careful, it can become a bit of a crutch for children. I've seen some really nice work done with a counting stick. So those that have never used one of these before, it's effectively a meter stick divided, or roughly a meter stick divided into 10 sections. And then you can use the points of division along that stick as particular nodes for each of these multiplication facts. That's a really nice thing to do, because you can start to then bounce around the multiplication facts a little bit. But I guess the thing I'd want to say is that I don't think the connection is actually as strong as people will often portray it in their teaching. I think getting to the point where you can recall multiplication and division facts often requires a leap of faith that intentionally goes beyond skip counting, because the temptation when you're doing 7 sevens of 49 is to go 7, 14, 21, 28, rather than trying to go straight there, which is obviously the end goal. However, that said, one thing that skip counting does do nicely is that it emphasizes this conceptual idea of multiplication being, or one way of being able to think of multiplication is as repeated addition. So that's one thing that skip counting does. When we're saying 7, 14, 21, 28, etc., we're emphasizing this idea that 4 sevens, or 4 multiplied by 7, literally is 7, and then another 7, and then another 7, until there are 4 lots of them. So it links on a conceptual level, and it does bring this idea of repeated addition. But in terms of the actual committing to memory of multiplication facts, it's connected, but in some ways it's a connection that we have to begin to, if not break, it's one that we have to, there's a reliance upon skip counting that we have to decrease.
I think we can assume that listeners will be familiar with the counting stick, because in tackling misconceptions, I reference and sort of point people towards, I think it's Jill Manser, Mansergh, and she has a group of teachers, I think it was at the Association of Teachers of Mathematics conference, learning their 17 times tables with the counting stick, and she does a brilliant job, you know. So obviously everyone will have read that book, and so will have seen that reference and seen that video. Our high quality textbook has skip counting built into the sections of multiplication. So in year 3, maybe year 4, you can expect to do some skip counting. They've got like sort of physical cues that match up with those. And I've always wondered, well, why are they doing this? You know, what is, because it then moves into sort of problem solving with multiplication. And I fall on the side of the patterns and taking the time, you know, saying that it is important to look for patterns in these tables, because some children, you know, with sort of certain prerequisites, will begin to see how the tables behave. And, you know, there are many patterns within the tables. And I think even if we just give them a couple of weeks, you know, I wouldn't skip count every table in a row. You know, you're learning about your 3 times tables. Let's start with some skip counting. It's a chance to explore what things look like. You know, it's almost like Vicky Priddle during Maths Chat Live was exploring counting, and we started counting from different starting points, changing the order, how many we want to count, and the patterns changed with those. And you can almost make these generalizations. And I think, you know, definitely you don't want to rely on skip counting, you know, because it takes more than 6 seconds to skip count some of the most important tables. Really, what it is, it's an opportunity for you to spend some time thinking about the big picture, I think. Because other than that, and on what you've said, Chris, the connection isn't as strong. Certainly it's not as obvious to teachers, I don't think. You know, so I think important, but the relationship between learning and skip counting isn't as obvious as perhaps other relationships are in the teaching of mathematics.
And there's definitely value, as you say, to skip counting sort of for its own sake for this pattern spotting, particularly where those patterns are more immediately graspable, for want of a better phrase. So this, so like when children are learning their 5s, great, it is a perfect example of a really nice, clear pattern, or learning their 10s, learning their 11s, 7s, less so. I mean, there's still patterns in there, but the patterns there are likely to relate to things like spotting how the bonds to 10 are still functioning. So when they're going 28, 35, noticing that it's like, oh yeah, so that reminds me of 8 add 7 brings me on to, you know, 15. So 28 add 7 is 35. I can see how that 7 splits in the same way. So there's this wider pattern spotting that's in there. But on a more general level, obviously your 5s, your 10s, your 2s, your 11s, your 9s, they have these lovely patterns that can allow for a sense of exploration that is valuable beyond just, you know, just learning of multiplication itself. You can begin to start thinking about just, you know, pattern spotting. You can start to say, you know, what do you notice here? Why is it the case that the digits in the 9 times table add up to 9 all the way across? Why is it that each time the 1's digit is becoming 1 less while the 10's digit becomes 1 more as we count forward? So there's value there when it comes to skip counting for all of these fantastic things, but the value that it brings to the learning of and the memorization of multiplication facts is perhaps not quite as strong as we might think. A question that comes up on Twitter occasionally, and it's the sort of question that lights a fire under me because I love this stuff, is what do you consider to be the best order? I mean, obviously there's a sense of subjectivity to it, but what do you reckon? Where do you begin with multiplication facts, and where do you end?
There seems to be a generally accepted order. People seem to think that 2, 5, and 10 are suitable for Key Stage 1. And then what you have perhaps the 4s, then the 8s, 3s, 6s, 9s, 7s. I mean, the 11s probably should have come earlier in that list. And then you finish with the 12s. I personally, unless I'm going to explore the field axioms, I don't really mind, because considering your 8 times tables, your 4 times 2 times tables, I think can be really powerful. Whenever, say for instance, I'm teaching year 5 or 6 about a longer method of division, I will often talk about how the 24 times tables, well, you know that because you know your 12 times tables, and it's your 12 times 2 times tables, and I'm really just giving them a shorthand for a much bigger generalization. And I think if you do those in tandem, then the sequencing makes sense because they build. But if we're making a distinction between memorization and understanding, then I perhaps think it's less consequential than the established way of doing things might suggest. I'm happy enough to wait until year 3 before any consideration, but I also would only introduce formal written algorithms for addition and subtraction in year 3. I would shift a lot of the sequencing if I were given the chance. So I don't know, maybe I've got one of my typical left field sort of fringe views on this kind of thing. You might say, no, Kieran, actually you need to go and have a look at this again. I think what's most important is identifying those facts which are unique and sequencing them in a way which is manageable. And I think we may get to this in later questions, but we've identified 37 unique facts that need to be committed to memory. And if you took those 37 facts and you did one a week and you allowed for some sort of variation, I reckon by the end of the first term in year 4, say you started in year 3, by the end of the first term in year 4, you could have memorized the unique facts. So I think for me, that's more important.
I think for the reasons spelled out earlier, I agree that you want to build confidence and start with ones where the patterns are most obvious. I think the 10s are the most sensible place to start because understanding your 10s ties in with an understanding of place value. I mean, all arithmetic ties into an understanding of place value. This idea of reorganizing numbers into how many 10s, how many leftovers, which is what we're doing with a lot of arithmetic, or all arithmetic, dare I say. So yeah, starting off with 10s because it supports place value. Obviously 2s and 5s have particular utility, and also children will have often learned doubles themselves before they've kind of thought of them in this way of 2, 4, 6, 8, 10. So 2s are there, 10s are there, and it makes sense. 5s have a very easy to recognize pattern, so great for skip counting. So I think that's definitely a sensible place to start. I think what's interesting is where I've seen people order these differently to the way you suggested. It is 11 that they move. They move 11s to earlier based on the assumption that, well, we're ordering them based on how difficult they are. We just want to start with the easiest and finish and give children more time to just mature cognitively before they tackle the most challenging ones. And 11s all the way up to 10 11s have a really nice pattern. So let's take advantage of that. Whereas I prefer 11s and 12s later, because in terms of utility, you only really need to know up to 10 times 10, and then you need to be able to use them and understand that the field axiom we've already mentioned a couple of times, this distributivity of multiplication over addition. For those people who aren't familiar with the field axioms, that's just a fancy way of saying that if I want to calculate 6 times 12, say, I can think of that as 10 times 6 and 2 times 6, or I can think of that as 7 times 6 and 5 times 6. Another example would be, let me pick another multiplication fact. If I'm doing 15 times 4, I can do 10 times 4 and 5 times 4, or any combination really of that 15 broken into 2 chunks, both of those parts multiplied by the 4 and then added together at the end. It's the idea upon which, or one of the ideas upon which all of our written algorithms and all of our understanding of arithmetic that goes beyond multiplication facts will be based upon. That's the reason why, in some ways, we only need to learn all the way up to 10 times 10, and then we can apply that to any multiplication fact that we like. So this brings me on to multiplying by 11, multiplying by 12. Those sets of multiplication and division facts, for me, are a way of reinforcing this understanding of that field axiom, of reinforcing distributivity of multiplication over addition. I want to use it as an opportunity to deal with the area model of multiplication again. So where does that come? Well, it comes in the sequence where I want to introduce this idea, which for me is probably at the end of those. This is not to say that this is the first time they've dealt with distributivity of multiplication over addition, but I want them to deal with this idea as a way of saying, look, now you know your multiplication facts, this is what you can apply it to. You know your sevens, and fantastic, you can use that to do your 17 times table. Your 4 times table, well, we can use that when we're multiplying by 14 or 34, or whatever it might be. That's why I tend to have 11s and 12s at the end, because I'm immediately thinking about, okay, we've got this body of facts. How can we apply them in a way that goes far beyond just those multiplication and division facts that we've learned?
I think I can definitely see your way of thinking. And, in a more sensible mood, where I'm not trying to challenge the orthodoxy as much as I appear to want to during this episode, I probably agree with you 100%. And I reckon if you went into my schools, you'd find something similar taking place, so it makes a whole lot of sense. Now, we've been itching to get to the next bit, pretty much the whole way through this episode. What strategies are particularly useful for learning them?
I think it can be tempting to consider the need for practice and then just to go, okay, well, here is a sheet of questions, work your way through them. And I don't think that is on its own a particularly good strategy. Equally, I think the idea of saying, oh, well, we always need to attach it to meaning. It has to be, and I'm going to be very careful what I mean by meaning here, but this idea that it always has to be attached to some kind of strategy. So if you're multiplying by 9, it always makes sense to multiply by 10 and then remove one lot. Well, that's one way to do it, but ideally I'd like you to be able to go straight there, over time at least. So something that kind of isn't quite either of those two things is flashcards. And by flashcards, I mean anything that brings up a question that has within it a sense of, a low pressurized sense, admittedly, but a sense of time behind it, a sense of, if you're not sure, take a guess. If you're wrong, you'll get feedback. That's the key thing. It's, here it is, have a go quickly. Did you get it right? Here's the right answer. And ideally, some kind of mechanism through which more practice can be devoted to the ones that aren't quite right. So one way I've seen that done really nicely in a classroom is set of flashcards that relate to multiplication facts that a pair of children have, and they go through them where one partner asks the question, and if they get it right, it goes on one pile. If they don't get it right, it goes on another pile. And when they're finished, they pick up the pile that they didn't get right, and they ask those ones again. So they come round again until this pile of ones that they don't get right gets smaller and smaller and smaller. You just cycle through that for 3 or 4 minutes, and then you switch. And there's no, giving of, oh, I got 20 out of 20. There's no big test or anything along those lines. It's just a chance to practice. What I like in particular about that is that because it's low pressure, kids who might otherwise be going, they get 7 sevens and they might be going 7, 14, 21, 28. They might be counting up. That low pressure situation and the chance to go through lots of them, they're quite quickly going, is it 49? And their partner's going, yeah, it is. And so there's this, that jump that I mentioned to having, I think I know it. Let me have a guess at it. The jump to doing that as your go-to strategy is bridged through sensitive use of flashcards. This being as low pressure as possible, zero pressure is essential, but you do need something in place that is gently nudging children away from counting up effectively, or always thinking of, oh, I want to rely on a strategy that I'm already very familiar with. Because to an extent, you do want children to go straight there. You want it to be something that's on the tip of their tongue. They can just go poof, and out it comes. I think there are online bits and pieces that obviously do this job. Hit the Button is online, it's free. I have seen children who will tell me that they hate multiplication tables, just become expert at them from coming in out of the cold during playtime to play Hit the Button for a few months. Yeah, a lot of my children get very good at multiplication tables the colder it gets, because I used to just say, look, if you want somewhere to sit out of the cold and play Hit the Button, you can, but that's the one rule. If you're in my classroom at break time because you're out of the cold, you're either playing Hit the Button or you're reading a book. And so, yeah, it was often the winter where kids got good at multiplication and division facts and improved their reading. So obviously can't talk about this without talking about Times Table Rockstars. Really, really useful bit of kit. I did say I was going to go back to meaning as well, though, and I mustn't forget this. I think that we often talk about learning with mathematics facts, and there's this dichotomy between rote learning and learning with meaning, where we think of learning with meaning as connecting it to a strategy. So like I said earlier, answering 7 8s by working out 10 8s, then subtracting 3 8s, for example, or working out 5 8s and then adding on 2 more lots of 8. And that's meaning. And then the other end of the spectrum is, here's the fact, no understanding behind it, just answer it. What this reminds me of is when a new child comes to a class. And when a new child comes to a class, they've got 29 kids' names to learn. And they learn them within a couple of weeks, they know them. Now, they're not connecting that to any underlying sense of meaning. If they spot another child in the classroom who's called Hannah, they're not on some level going, oh, well, I see why you're called Hannah. It's because you've got blonde hair. There's no like underlying connection there, but that doesn't mean it isn't meaningful. It's still meaningful because this is a person's name they want to learn. This is someone they're going to interact with. This is something they're going to use. It's something that's going to have purpose. So there's that sense of meaning that isn't necessarily always worrying about the why. It's meaning that comes from the fact that this is going to be useful, that it's going to have value. And I think there's that sense of meaning is important to multiplication facts. The fact that children learn them, and then we're showing them why they're useful. We're showing them why they're valuable. We're showing them how they're going to use them in lots of different contexts. I think we forget about that sense of meaning and assume that isn't as important as the understanding the why behind a given set of multiplication and division facts.
That's the perfect analogy. That's brilliant, because I think a lot of the misunderstanding comes from not understanding, stuff Dan Willingham talks about, inflexible knowledge, and rote learning gets a bad name because it's actually been mislabeled, so I think anything we can do to sort of clarify that actually there's a time and a place for this, but listening to you speak, if we think about the experiment that Hermann Ebbinghaus did on himself in the late 19th century, he was memorizing a bunch of nonsense words with flashcards and then increasing the distance between the opportunities to retest himself until eventually he committed these nonsense words to memory, and that study's been replicated, I think, 11 times, most recently 2015. The same principle applies for these tables, and they're not nonsense. So why wouldn't you, And like, see the point you were talking about where you just have to trust yourself, is this 49? There is a method of committing vocabulary to memory. I think it's called the gold method. It's well worth Googling. But essentially you start with these lists. You make a list every day, say 36 words. And then in 2 weeks you come back to it. And you have to cut the words you don't think, or that you don't think you need to keep in the list anymore. The words you think and there's no testing yourself on it, I don't think, or certainly if you do test it, you have to trust your gut. And then that's how your list gets smaller. So you start off with the bronze list, then the silver list, then the gold list, until you've only got the words that you can't remember, and like I've tried, I can never get the whole way through this list, but I really, at some point before I die, would like to test out the gold method in full to see if I can, commit a Portuguese dictionary to memory. I'll obviously do other stuff on the side, but in terms of vocabulary acquisition, I was having a conversation with a Spanish teacher about education, and I was using words that after the conversation, like, well, when did I learn that? And then I remember that 3 years ago, I spent a lot of time with flashcards committing stuff to memory that is only useful now that I put the rest of the syntax and the grammar together. And I think, yeah, so everything you said there, Chris, all I was thinking about these other instances where things are worth committing to memory. That's the way to approach it, and you don't need much. You just need time and to be consistent, because 5 minutes every day of the week is much more preferable to 6 hours one day a week or 6 hours one day a term, and I think, having worked in schools in areas of socioeconomic deprivation, high disadvantage, there's a big distinction between those pupils who do this kind of memorization at home as well as in school. And I think where we aren't fortunate enough to have those kind of opportunities for our pupils, I think the school almost needs to be the surrogate, and to make sure that they're putting those principles at the heart of everything they do, because those children in particular need to learn these tables, because they need to be successful in mathematics, because it's the difference between a C and a D at GCSE, which I think I mentioned the review of later earnings. That's the biggest difference maker. The pupils who get, well, what would be now, a 4 or a 5? Those pupils will earn more than those pupils who score a D and below. And, that's a big deal. So I think, if we go all the way back to why these are essential, this methodology, this pedagogy is essential, because we're almost going one step towards guaranteeing that these pupils will have a successful life later on. So I don't think, in terms of strategies, I have much to add. What we've done is, like I said earlier on, we have taken unique facts, asked children to commit 1 fact a week to memory, and then built almost like retrieval roulette, where Adam Boxer's got these sort of science-based questions, and you can decide which range you want the questions to be randomly generated from. We do the same with times tables. So you can choose, okay, well, we're 5 weeks into the term, let's test the first 5. We're 10 weeks into the term, let's have 5 of the first 10. And so hopefully after 37 weeks, children know the unique facts that we want them to know. We're not yet, we started this in September. It was thanks to Janine Allen at the Kent Medway Maths Hub that this sort of thinking came along. And we do lots of representations, lots of sort of back and forth repetition, call and response. But ultimately, you've got 1 fact to commit to memory, and you're going to be tested on those facts regularly, so that hopefully we can apply what we know about committing things to memory. But like I said, I'll report back on that after a year, 2 years, to see if that really does have the impact I believe it will.
Thinking back to the method you described there, it reminded me of something that I like to do with multiplication tables, which tends to be a sort of stepping stone between counting stick and asking children to use flashcards or to support each other with flashcards. It's so you've done your counting stick, you're pretty solid with skip counting, etc. What I like to do is write the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the board, And then underneath that, write, let's say we're learning our 7 times table. So beneath 1, I write 7, beneath 2, I write 14, etc. So children can see the links. They can see, well, that's the answer to 3 sevens. That's the answer to 5 sevens, etc. You put them on the board, and then at first you say to children, okay, so what's 3 multiplied by 7? And they can just read it off the board like it's a table. Oh, well, 3 sevens are 21, etc. And then you do that for a little while, very brief period of time. And then you say, okay, which ones don't need to be there? Which ones do we know? And you rub off the underneath the number 1, you rub off the number 7, because everyone knows 1 lot of 7. Everyone knows 10 lots of 7 is 70 as well. So you rub off that one. And then you say, well, and is there any others we know? Okay, let's rub off the 2, let's rub off the 5, stop there, let's keep going. And then you start asking random questions around the room. Okay, write on your whiteboard as quick as you can, what is 7 sevens? What are 3 sevens, etc. And you do that. And then you ask another child around the room, say, okay, we're going to remove another one. Which one are we going to remove? And you go through that step by step, removing them from the easiest ones. And you can do that sort of within a lesson, but you can also do that across a week. So you're doing lots of familiarization with that multiplication, with that set of multiplication facts. And then from that, what you're then doing is you're also removing them from the board, so that over time, they've just got nothing. They've just got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And maybe the only one that's there is 8 sevens, because that's one they're really struggling with. But because that's there, and that's the only one there, by the time it's rubbed off, 8 sevens is absolutely committed to memory. That's one way to transition towards the use of flashcards, assuming you are introducing them as a set rather than as kind of you're thinking they're like 1 fact a week. If you're introducing, we're going to be learning our 8s. Linked to this, of course, is, okay, so you seem to be talking about multiplication facts. How does that work in terms of division facts? Well, I don't know about you, but my knowledge of, in terms of if someone says to me, what's 56 divided by 8? I'm thinking, what do I multiply by 8 to get 56? I'm not really I am doing division, but I'm doing division by thinking about the inverse process. I'm thinking, what do I, in the same way that with number bonds, if we're talking with children, it's like, what's 15 subtract 9? Once children learn that is really asking, hang on a minute, it's really just asking you what goes with 9 to equal 15. They find subtraction significantly more easy when they've embedded that. In the same way, I just think, let's embed the multiplication facts and then give them that understanding, that strategy of saying, look, now you know that 7 8s are 56. If I ask you how many 8s are in 56, I'm really asking you how many lots of 8s are, what do I multiply 8 by to get, rather than thinking of them as a separate thing. I know that sounds quite obvious, and yet I've seen people try to teach them as, oh, okay, we're going to learn the multiplication facts for this, and then we're going to learn the division facts, without explicitly explaining to children the link between the two. So yeah, I just think get them, unless I'm mistaken, the as well, and I imagine this is partly why, the multiplication test check, multiplication table check in year 4 is just the multiplication facts, isn't it? It's not the related division facts, which kind of makes sense, because once you know those multiplication facts by heart, then you can, derive the related division facts relatively easily. I know that's for certain how I learned them. I got to year 6 not knowing basically any of them, and I had a teacher called Mr. Deakin who was just stunned by this fact, and just he actually just made me fill out a multiplication grid. So one that literally had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across the top, and then a random distribution of 1 to 10 down the side. And I just had to fill it out every day. And after a few months, I could just fill it out. And I learned my division facts not by doing anything else. It was just him saying to me, look, you do recognize that now you know these multiplication facts, you also know the related division ones. So we've talked about multiplication facts, division facts, how we might learn them and embed them. Is there an argument that in the time children spend at primary school, we should have higher expectations for what they can do when it comes to the use of multiplication facts mentally by the time they leave?
For me, there are almost 2 parts to my response. The first part is that if we get to this utopia where our pupils have memorized the facts before they go into upper key stage 2, and are then given really rich opportunities to develop their understanding of mathematics and to manipulate the mathematics and play with it to the point where they're able to, they sort of have this internal sense of the generalizations that we want them to hold, then I don't see why we can't expect almost this next level of manipulation. In the same way that we want our year 2 pupils manipulating addition and subtraction really fluidly. You know, sometimes when you show teachers the different mental options pupils have, they're like, wow, this is phenomenal. You know, I really want to get there. And I think the same is true of manipulating multiplication and division. So I think in an ideal world, if we ever do get there, or certainly even within our own classes, if we get a class, you know, I've never taught a class where all the pupils knew their times tables when they came in, you know, so it's not my norm, which is why I'm calling it utopia. And I think, you know, a lot of people will see the reflection of the pupils they teach in that. But I do think it's definitely possible. The second part of the answer is that we need to sort the situation that we're in right now, where essentially too many pupils don't have a grasp of those essential facts. And I think the profession I came into, you know, nearly 15 years ago, not much has changed on the ground. I see the same situation. I hear teachers telling me the same things. You know, I certainly remember my first class, it was a year 5 class, and thinking, if only they knew their times tables, this would be so much easier. You know, not to mention that I was an NQT and didn't have any sort of natural propensity for teaching and managing classrooms, but, you know, the mathematics would have been easier. And I see that day in, day out, and have had that conversation with people. When I'm supporting teachers and we're talking about the teaching of fractions, it goes back to times tables. So I think absolutely, in a world where we have all pupils with a sort of a command of what they need to, it's definitely possible. But I think our priorities are different in this very moment. And I hope that that will change soon. But in my gut, in another 15 years, will I still be saying the same thing? I don't know. Am I being too negative?
I suspect you're right. I think there is an extent to which we will be aiming to get every child, or as many children as possible, knowing their multiplication and related division facts by the time they leave primary school, you know, however many decades from now it is when we retire. That said, I think maybe this is just, I think maybe a reason I brought up this question is a chance for me to pontificate a little bit, because it does bother me somewhat the amount of time that we spend on things like long division and 2-digit by 4-digit multiplication with a written method, and you get children mastering that stuff, and then you say to them, okay, so what's 7 lots of 16? And it's written down for them, and they're automatically going for a written method. You think, well, no, hang on. What's 7 tens? What's 7 sixes? I know you can add 70 and 42. So I think there's just so much more power in mental arithmetic and those kind of basics of mental arithmetic that, yeah, it frustrates me that we dedicate so much time to written methods and so little time to mental arithmetic, especially given the world in which we live. Calculators are not going to cease to exist, and mental arithmetic is still always going to be relatively useful, whereas written arithmetic, not so much. I would love a situation whereby we reintroduced calculators into primary school for certain things, took away some, not all, but some of the teaching of written methods. I'd want written methods to be taught as a way of understanding place value, a way of understanding how we organize and deal with numbers, rather than, oh, I've got a long division method. As soon as you're dividing a 4-digit number by 27, what are you doing? What world are we living in where that is a useful, formal algorithm to have memorized? Spend that time on learning how to multiply 2-digit numbers by 1-digit numbers, because in some ways that's just also a more interesting bit of mathematics to do. Understanding, again, go back to it, really getting to grips with the distributive principle and getting to grips with adding together numbers and subtracting numbers, that kind of stuff is based upon. But yeah, you're probably right that we will end up focusing on just the core facts that we've described up to 12 times 12, or dare I say, up to 10 times 10 if we're focusing really on utility. But I'd love to see a situation where we raised the bar for what we expected for mental arithmetic, but including related to multiplication. And if that meant getting rid of some of the written arithmetic that is currently, to some extent at least, cluttering up the curriculum, that would be no bad thing, I think.
I mean, I think we set out for aiming for a short episode, and it looks like we could talk for another 3 hours, Chris, on multiplication tables. All that's left to say is thank you very much for joining me.
Thank you for having me. It's been a pleasure.
I'm sure this won't be the last time that we do visit this topic. And everyone at home, until next time, thanks for listening.